Hello guys, hope you're doing all right. We couldn't have our last lab, so I'm going to record this. This is all about k-means, and you all know k-means algorithm and how it works. So just like always, we need to import some libraries. We need pandas, numpy, and matplotlib. And the tutorial that I'm going to go through is from this source. I will provide you with the data set. It's all about sales information from 200 customers. We have their age and annual income and also spending score. So this is the data set. I need to read that data set first. And this is the information, description of the data. So for the sake of simplicity, and as we need to have just 2 dimensions, I'm going to choose only 2 columns from this data set, which is the third column, annual income, and the fourth one, spending score. So with iLog, I'm filtering all of the rows with only 2 features, and I'm converting it by doing dot values. And what dot values do, it's actually converting this data frame to NumPy array, because I'm going to work with NumPy array. So this is my data set. So my current data set has 200 data points and 2 features. Okay. The next step is storing the number of training examples, which is M, 200 for this data set. And N is like the second dimension of shape, which is the number of feature, which is 2. And also we need number of iteration, and we're going to use this later on. So the next step is to choose the number of clusters. You know that this is a hyperparameter that need to be tuned. For now, we are not going to do cross-validation or any validation procedures to fine-tune the value of this hyperparameter. We assume that we have 5 clusters, but later on, we can see a method that we will use to validate the value of k. So for now, we consider k as 5. The first step in this algorithm is to consider a set of initial centroid. So, you know, the centroid are the centers of each cluster. So now that I have 5 clusters, I need 5 points with like 2 dimensions. So basically, centroid is a matrix of shape n by k, and n is 200. I'm sorry, n is 2. So I have 2 features, and I need k points. So it's gonna be 2 by 5. Okay, so my initial centroid for now is a empty array, MP NumPy array, and I'm reshaping it as n by 1. Why I'm doing this? Because later on we are going to concatenate some columns to that, and this is why we choose 0 as the second dimension, such that we could append or concatenate another column to that. Okay, so for the beginning, that's a empty NumPy array, but in the following, we are consider these centroids to be random points from the data set itself. So basically we are choosing random points from the data points. But how? By doing this. So I need k points. I generate a random integer number between 0 and 109, because I'm going to choose one of the indexes from my data points, okay? And I will use this random number to choose one of the data points by doing this. So I'm basically filtering. I'm choosing the data point with the index rand from my whole data set, okay? And by np.c underline, I'm appending or concatenating these two columns together. So centroid is empty so far for the first iteration, and then we append a column to that. For the second iteration, it's like the second centroid is going to add another column, and it continues until we reach 5 centroids. So far, I have my initial centroids that are randomly chosen points from the data points itself. The second step is that we need to compute the Euclidean distance from all of the data points, okay? And from the Euclidean distance between all of the data points and between all of the centroids, and then calculate the minimum distance and assign the cluster based on this minimal distance. So first, I need to calculate the distance matrix and then choose the closest one and assign that data point to the closest centroid, okay? So this is basically a step 2.a, okay? The output of this algorithm is considered to be a dictionary with cluster numbers as keys and data points that belong to that clusters, okay? So for each key, we have like the number of clusters, and the value would be the assigned data points. So for first, we have an empty dictionary, and we need a Euclidean distance. For now, it's an MP array with shape of M and 0, because just like before, I'm going to append some columns to that. And so this is it. I just forgot to mention something here. This function is just like concatenate. But when you're going to use concatenate in order to stick two columns together, you need to pass two input, two columns together, and also an axis 1. Axis 1 allows you to stick that column wise. But np.c is like concentrating alleys along the second axis. So in terms of like a matrix of 2 dimensions, it's going to be columns, okay? So far, I have an empty output. I define the Euclidean distance. And now, by doing this, I'm calculating the Euclidean distance of all the data points, okay? Just like this. In the first iteration for the first centroid or for the first cluster, I'm taking the difference between all of the data points, which is 200 data points, and the first centroid, okay, to the power of 2, and sum over all of the columns. So that would be sum of a squared distance, okay, sum of a squared distance between each data point and the first centroid, okay? So that's basically a squared distance, a squared Euclidean distance, and we can continue with that because getting the root or not doing that are basically the same, because we need to compare the distances only. Okay, so I store it in the temporary distance, and then I stick or concatenate temporary distance to Euclidean distance. So far in the first iteration, I have the Euclidean distance of all the training data points to the first centroid, first cluster, first centroid point. I continue calculate it for all the centroid. So I end up, for the Euclidean distance, I end up with a matrix of shape this M multiply K. So each training data point have a distance from the first centroid, second, and so on, okay? In the following, I need to have I need to calculate the argument. Why? Because I want to know which cluster is closest, which centroid is closest for each data point. And after that, I need to, and I do it column wise because columns are like clusters, and I will add 1 to it because it's gonna be 0 to 4 plus 1, it will change to 1 to 5, right? So having this, so far I have calculated the distance and I choose the closest centroid. Now I need to fill my empty dictionary, which is the output. We define this as a dictionary. So for doing this, I'm basically iterating. I'm doing it in a loop over the number of clusters, and for each clusters, I need the index. I need like the first cluster index is 0. So I need to add 1 to it. Okay. So this is like this. All the points for key k plus 1, for example, it could be key equal to 1, which is first cluster. For now, it's an empty array of shape 2 by 0, just like before, because we are going to add columns to that, and all of the data points has like 2 features. So considering this empty dictionary, I would end up with something like this. See, I have 5 clusters as my keys, and also there's a numpy array showing all the assigned points to that specific clusters. Okay, in this line of code, I'm going to assign points to that and group all the data points in the assigned clusters. By what? But how? By doing this. So this time I'm going to iterate over the points. I find the index of the points and I'm going to assign that to the cluster I want from the vector C. What was vector C? Vector C was showing the closest clusters to each data point. So basically, here I'm giving the key. So for example, the first point is gonna be, I can even show you here, like what is C? Look at here. So the first data point needs to be assigned to cluster 1. So once I implement this line of code, for the first iteration, it's gonna be C0. C0 is 1. So it's basically 1 is showing that the value for the key equal to 1 would be this. And what is this? It's going to concatenate the same data point, which is x0. So x0 is the associated point with row 0, and it's going to concatenate this column to the previous values. So completing all this iteration, we would end up with a dictionary that has grouped data points for each clusters. Okay, so let's see that. What is y right now? See, for example, y1. For these clusters, this is the assigned points, right? See, there is this, all the assigned points, again, all the assigned points, and so on. And what is like, for example, the shape of this array? There's 90 points assigned to the first cluster. Second cluster's 31 points. Okay, so all of the data has, so in this like matrix, you need to consider that points are in columns because we have 2 by 31s. And this is why we need to take the transpose for y. If I implement this, you could see, okay, this is vice versa now. It's better because we always want rows as the number of data points, right? Okay, so far we did great. And now we are ready to apply the next step. What is the next step? It's updating the centroid. So now that I have grouped all the data points and assigned them to their associated clusters, I need to calculate the average of them and update the new centroid equal to that average. So for each clusters, I'm taking the average over rows because I need one vector having 2 values, okay? This is the average, and I will assign this as my new centroid for each cluster. So this is the update step, okay? We have done all of this only for one iteration. The thing is that when our algorithms need to be converged after doing a specific number of iteration. And one of the famous stopping criteria is limiting the number of iteration. You remember we considered number of iteration equal to 100. So we are going to apply all of these steps in a loop equal to the number of iteration, okay? And by this, we expect our algorithm to be converged, okay? Now, okay, so basically, it's all the same steps. There's nothing is different. We only put it in a loop, okay? So now we can visualize this. Having our initial data points, the first column, which is income, the second column, the number of transactions, it's going to be in black, and label and title of the plot. So this is the unclustered data. This is all the training data points. Nothing is clustered yet. But from the appearance, we can guess that there might be 5 clusters. So we are not far away from expectation. So this is probably a good choice for K to be 5. But later on, we're going to see a method to validate this hyperparameter. So the next step is to plot the cluster data. But how? So we have all the clusters, we have all the data in output. If you take a look at here, the output was Y, and now in the end, I'm storing Y in output. So output is the same dictionary. So it's in a for loop, considering for each clusters, I'm taking the values, the first column, the first feature of the values, and the second feature of the values. And for each cluster, I'm choosing a different color. So this is how it appears here. See? So the big yellow dots are the centroids, and here you can see our 5 clusters, and it's very reasonable. There is so many insight from this plot. For example, there's people with low income and low number of transactions, low income and high number of transactions. This is this clusters. And for example, the company may want to offer them some promotion, or there is a stingy ones here with the high income and low number of transactions. So the basic goal of unsupervised clustering is to gain insight from the data. Okay. As I mentioned earlier, we need to find the appropriate K. Our initial guess might not always be correct. So we need a method to validate the value. One method that is used commonly is the elbow method. In the elbow method, we look for a clustering that has the least sum of a square of distances of every point from its corresponding cluster centroid. Okay, so we need to calculate after doing all the training. So after that, we have all the clusters. We need to calculate the distance of all the data points from their associated centroid. And if you sum this distance, that could be sum of a square of distances, we need this value to be as low as possible. But the thing is that the lowest value for this sum of a square of distances can be 0, because as we increase k, this function of error will be increased. If we have, for example, 200 data points and we set k to be 200, what does it mean? It means that we have 200 clusters, and all of the data points would be a centroid. Therefore, sum of a square of distances of every data point from the centroid would be 0, and it's not at all desired. Okay, so this is why elbow method is defined. So elbow method is basically saying that increase k such that you can decrease sum of a square of distances, but stop when there is not significant decrease in rate when you increase data, when you increase like k. So in the plot, you will see there is a elbow. Once you reach the elbow, there's a bend. Once you reach the band, it's an appropriate number and it's better to stop. Okay, and how we calculate the value? The value that is calculated is called WCSS, which is within cluster sum of a square. So the distance value of all data points from their corresponding cluster centroid is called like within cluster sum of a square. So we calculate this cost, and we plot this cost based on the k, and once we reach a knee in the plot, we can stop and we consider we basically have found the best value of k. Okay, so for doing this, after doing this elbow method, I have just created the k-means method that we implement from scratch within the framework of a class. Okay, so again, nothing is very different from what we have done so far. It's just in the framework of class, of creating an object. So what is this? If we want to define the class for the k-means, this is how we initiate the object. For this object, we need to pass through the class the data set, the number of clusters. So I can have the data set. There is an empty dictionary as the output, initial centroid, which is again an empty array, number of k, and also the number of data points. There's a function defined as k-means plus plus, but for now, do not consider this. I'm going to explain it later. And in the fit function, we first randomly initialize the centroid, just like what we did. So if you want to do that, I need to comment this line and uncomment these lines, okay? So if you wanted to do that, for now, I'm not doing this. I'm just explaining the functions. Okay, so Consider that I'm going to initialize randomly, just like what we did. So we generate random numbers from the indexes of the data points and choose the exact same point as our centroids, initial centroids. After doing that, we need to compute the distances, just like we did before, choose the minimum distance, and then assign values to the dictionary such that we group the data into each considered clusters. Okay, so we have as the output y. For the predict method, we only have the output as the real output of the method and centroids that we have so far. And what is WCSS, which is the Witten cost sum of a squared? So this is the important part. For first, it's 0, but for each clusters, because it's within clusters, for each clusters, we calculate the difference of the assigned points to that clusters with centroid of that clusters, having it to the power of 2 because we are looking for sum of a squared error, and then have it sum, and then add it to the initial error. Doing this, I have the Witten cluster sum of a squared distances. This is the value that I'm going to minimize. Okay, so simply we have k-means as a class. Now we are ready to do the validation part. How? We need to consider a range with an upper limit. For example, the upper limit here is 10 because the last one is not considered. So it's basically the range of 1 to 10. And I'm fitting k-means and creating the object of k-means for this data point, considering each value of k in the for loop, and then do the fitting process with number of iteration, calling the predict method to have the final centroids and the final output. For this final output, I'm going to calculate the cost. Okay, so consider this line, which is appending the cost for each iteration. Okay, so doing this, I would end up an array with all the values for each k. Okay, so this is it. So I have the values of k. This is my x axis, and the y axis would be the costs and label and titles. So this is it. See what I have here: number of clusters, the value of the error, and as you see, there is an incredible decrease in the beginning of the plot, and then there is a bend here, and after that there is not very significant decrease in the error. So once I reach this point, which is exactly at 5, I can consider this as an appropriate value for k, right? Okay, so we saw that k equal to 5 is the best observation. Using this best observation, I can fit the model like this, okay? And again, plot the result, which is this. So we did great so far. Now, what is k-means plus plus? The lines of code that you saw here in k-means plus plus initialization. K-means plus plus initialization is another method of initialization. As you remember, we consider random points from the dataset itself for our initial centroid, but there is a problem with this method. If the random points are close together, we need a lot more number of iteration to converge. So this is one problem with this method, and it's not a good method. There are another method that is considered to solve this issue. One of them is K-means plus plus. What does it but how it's acting is like this. In K-means plus plus, we consider the first centroid randomly. But for the other ones, like second and the third, we are going to choose the ones that are further away from the first one, or from the first and second, for example, if you're going to choose the third one. So how we do that, we consider a probability distribution for all of the points, and the points that are further away from current value of centroids are having higher probability of being chosen. Okay, so there are more potential to be the next centroids. So this is basically the logic behind this algorithm. Okay, and there is actually some step. So for doing this, randomly select the first cluster center from the data points. Then loop over the number of centroids that need to be chosen. So we have the first one, we're going to loop over the rest of them. For each data point, we need to calculate Euclidean distance square from already chosen centroids. It could be already chosen centroid, could be 1, 2, 3, based on the number of iteration that we are currently in, and then append the minimum distance to a distance array. So for example, if I have 2 already chosen centroids, I'm going to calculate the distance of all the data points to these 2, and then choose the minimum distance between each data point to these 2 centroids and put it in a distance array, right? Okay. Then I need to calculate the probability of choosing the particular data point by dividing this distance area to the sum of distance array. So I calculated distance array. So I have a distance array which has 200 elements for this specific data set. For each data, I calculate a probability which is dividing the distance by the sum of distance array. So pretty simple. Each distance dividing by sum of all the distance array. So this is actually the probability distribution. After that, so you can see that if it's further away, it has higher chance of being selected. Okay. After that, I need to calculate the cumulative probability distribution. Then choose a random number between 0 to 1. Get the index I of the cumulative probability distribution, which is just greater than the chosen random number. So once we reach the cumulative probability distribution, which is greater than the chosen random number, we need to stop and assign that data point as the next cluster centroid. Okay, repeat this process until we have K centroid. So between steps, this is like this. For the first centroid, I randomly choose one data point, one of the data points we already have. I loop over the number of clusters and calculate the distance between current centroids, each data set and the current data and the current centroid, sum of a squared. Okay, choose the minimum because it might be more than one centroid, and then append this to D. D is the distance array. Calculate the probability by dividing the distance array to the sum of that. So probability is still an array with the shape equal to 200. then calculating cumulative probability, which can be done by this function, cumulative sum, from NumPy, and then generate a random number. In this loop, we enumerate over the indexes of cumulative probability and the value of the array. And once we reach a probability which is greater than the random number, we stop. And we consider that a specific value, which is a specific index, which is j, equal to I, and I would be my next centroid, right? I think that's clear enough. Doing this for all the clusters, I end up with a complete centroid that includes all 5, if k, for example, is 5, all 5 points. And I store it in centroid temp, right? So I generally created a k-means plus initialization method, and using this temp centroid, I'm going to compare the random ones that we initially created with k-means plus centroid in this scatter plot. See how beautiful it is. Random centroids are the black ones, but k-means plus are the yellow one. See how close they are. You could go and try this on your own computer. If you consider these centroids, and you can just keep track of time, but by doing a time it. So you could definitely see that the convergence time of the algorithm for these initial centroid are way more than these ones because they are further away from each other. Okay, so this is it. The next thing that we are going to explore is to compare the k-means method that we created from scratch with k-means from scikit-learn library. So this is a scikit-learn cluster k-means. So we need to import that. Again, considering the within clusters sum of a squared error to find the best k. There is a range because you need to iterate over all the possible values for k. So we basically fit k-means, create the object, and then fit, and then append the value of the error to this MP array. And the value of WCSS is calculated by this feature from k-means, right? So doing this, we have like this plot. Again, it's telling that k equal to 5 is the best option. And in the end, when I'm going to plot the clusters, the output from k-means from scikit-learn is y underline k-means, which is achieved by predict, by calling the predict method. If you call the predict method, it's something like this, but it's different from what we had from our implementation. See, our implementation, the output from our implementation was a dictionary, but here it's an NumPy array, and it's considered the cluster for each of data points in an array. So basically, if you do something like this, you are filtering all the rows based on the clusters. So as the first 0 is the first cluster. So it's showing all the points from the data set that is assigned to first clusters, right? Which is 81 points. So it's somehow different, but with the same procedure. There's nothing different in the steps of the algorithm. Okay, so the output is different. So remember, you need to filter that based on the value. So you have all the rows from data point that is assigned to first cluster, second, and so on. Okay, and we plot them in different colors. So this is it. This is the output from KNN by scikit-learn. So just to sum up, in this tutorial, we covered how to implement k-means from scratch in a framework of the clusters. This is it. This is here. And I also convert this k-means plus plus as a function in the class of k-means, right? So we learned how to write it from scratch. We learned how to fine-tune the value for k as a hyperparameter, and we learned how to do that in scikit-learn library. I hope that is useful for you. It's very sad that I couldn't see your face and interact with you in our last lab. I really hope you could watch that and take advantage of these methods. It was my real pleasure to be with you in this course, and I really hope you like it all. And that's it. Thank you so much.